So I'm going to kind of give an overview. I call this the 30,000 foot overview of writing your own evolution code within the Einstein Toolkit. Okay, and just to kind of remind everyone, just to get it on a common starting point, let's assume that we're going to start with a hyperbolic system of PDEs, which are going to be first order in time. You can always make them first order in time. And we're going to discretize the problem by introducing a grid, and our fields will become grid functions on that grid. And the goal is that we replace spatial derivatives with finite differencing on the grid. And so our PDE becomes a set of coupled ODEs for the fields at every grid point. And we solve that with a standard ODE solver. Now, how that actually works, so how do we actually do that in the Einstein Toolkit? Well, first of all, we need to tell Cactus what grid functions we have. We need to also tell it, if we have a grid function, where to find the right-hand side. In other words, the u dot of du dt is equal to u dot. And we're going to need to write routines to actually calculate the right-hand sides. And we're going to have to somehow schedule those routines to run at the right time. And also, there'll be certain fine-tuning parameters which we'll need to specify, which will actually indicate what problem we're actually solving. And I give examples of what type of initial data, if you have some kind of damping, what kind of damping, perhaps what kind of finite difference order. And once you get that all done, you can start doing science with the toolkit. And there are plenty of caveats to that, but we'll get there. Okay, so I'm kind of describing the process for creating this thorn, which is called simple Maxwell. And perhaps I should just start off with get this link. And I'm going to just there's a link for you to see it. But basically, this contains the tutorial, and it's actually I've updated the tutorial for this workshop, so it's tutorial 2022, and the updates actually consisted of somewhat of simplifying it. So it's less feature rich, but at the same time, but hopefully a little bit more readable because of that. Okay. We'll get to this in a second. By the way, all the notebooks that I'm showing you, they're all actually in this repository. So here's the system I want to look at. It's a Maxwell. It's a slightly extended the Maxwell system. It's going to involve a standard.
Yosef,
Yep.
Sorry to. We have a question from someone here in person.
Sure.
I wanted to see that URL long enough to write it down.
Oh.
Ah, okay. 1 second. Now I got to find where I threw it. Okay, I'm going to get it again.
Well, could you put it, Yosef, could you paste it in chat maybe?
Yes, I will. Now I got to find it first. 1 second.
Co-host, and he has to dismiss the message.
That's all.
It's on his turn.
Yeah, it's just.
Okay, did I actually hit return? There we go.
There it is.
There it is.
Okay. Sometimes tiling window managers aren't as convenient as non-tiling. Okay. So this is the system I want to look at. It's just a standard Maxwell equations. Plus, I've added, just for fun, some damping terms here, the psi d and psi b. And it's just, if psi d and psi b are 0, this is just standard Maxwell equation. I'm allowing for an epsilon to be different from 1, and I'm allowing for mu to be different from 1. And these damping parameters, kd and kb, what they do is that if you have some constraint violation, kd and kb will actually cause the constraints to damp away. Technically speaking, it will be the high frequency components to damp away. And just having a psi b and a psi d by itself makes the constraints at least obey a wave equation. So in some sense, it's a better behaved system, but it's not really going to affect what we're doing over here. Okay. Now, we have two vector fields, B and D, so, and then two scalar fields. So ultimately, we're going to have 8 functions which we're going to have to evolve, which are just going to call Bx, By, Bz, and so on. Okay. By the way, this notebook, although, well, don't do this, but this notebook actually does generate the code, kind of, sorta. This is not NERPy. This is not nearly as good as NERPy. Use NERPy for this, but this will actually generate the right-hand side if you run it. Okay. Okay. But we'll get to that in a moment. First things we have to do is, now that we know what evolution system we want to implement, we have to start figuring out how to actually implement this. And the first thing I actually want to go over is not how to tell Cactus about what variables we're evolving, but actually, once we get to that step, how do we actually finite difference? And I ran into a problem. Okay, that'll do. Okay. So first things first is how do you finite difference something in Cactus? Well, first thing you got to do is you got to tell Cactus that the grid function exists. So I'm going to be introducing here as an example a scalar function, and it's going to be called f. And Cactus allows you to group things together. So I'm grouping this particular scalar field in a group called myScalar. Oops, I want that. Sorry. And I'm going to also store the gradient of this scalar as basically a vector field. And a vector really, as far as Cactus is concerned, is 3 scalars, but with a special type of this tag, tensor type alias is equal to u. So that just tells it that tells it it's a vector. As far as Cactus is concerned, unless you're talking about boundary conditions, it doesn't distinguish between vectors and scalars. Now, of course, if you're going to have a vector, if you're going to have grid functions, you have to declare storage for them. That will happen. You declare the variables in the interface.ccl. You declare the storage in schedule.ccl, but we'll get to that later. Okay. So now I'm going to show you a piece of Cactus code, and the goal here is to take a derivative of our function f. So first things first is we're going to loop over all points. So we're going to have an index k, which will be the z direction, j is the y, I is the x direction. And you probably notice here that indices don't start at 1, don't start at 0. That's because I'm going to be taking a derivative, and I'm going to be using centered derivative. So I have to start taking the derivative at the second point. I can't take it at the first point. And C indices start at 0. And then we're going up to CCTK LSH. The LSH is an array which tells us the size of how many grid points in each direction for Z, Y, and X. So, but the actual grid functions themselves, and I'll just kind of I want to skip this for just a second. The actual grid functions themselves are actually C one-dimensional arrays. So somehow these 3-dimensional indices, I, J, K, have to be packed into a one-dimensional array, and there's a helper function which does it for us. So I, J, K becomes a single scalar. I, J, K becomes a single scalar, which I call I, J, K. And then I'm going to define similar scalars for corresponding to I plus 1, I minus 1, J plus 1, J minus 1, K plus 1, and K minus 1. And then using second order finite differencing, the derivative, the x derivative would just be f evaluated I plus 1 minus f evaluated I minus 1 over dx. And similar for dy and dz. Okay. Now, just a little note as to why we definitely want to use this CCTK GF index object is because Cactus doesn't guarantees that the array will be big enough to store grid points, arrays of size LSH0 times LSH1 times LSH2. But it doesn't guarantee that the array isn't bigger. Okay, so for example, the first, the logical IJK000 might correspond to index 0 on the array, and 100 might correspond to 1. But there could be, after you get to the end of after you run out of I, you could have some padding. And so the next index over, where I is 0 and j is 1, might not be at position nx, but at position nx plus some padding. And that padding would be determined in general, you run a code which was completely agnostic as to whether that padding exists or not. And so there'll be padding at the end. There could be padding at the end of the x direction, y direction, the end of the z direction. So you shouldn't assume that the mapping between point ijk and the actual array index. Although there is a guarantee that the point I and the point ijk and I plus 1 jk are going to be neighbors. Okay. Now I want to talk about a few of the design choices that I'm making for the tutorial. And every one of these choices can be, in some sense, fixed. And there actually is another version that doesn't have these choices. Okay, first of all, let's not complicate ourselves with an external boundary condition. Let's just assume we're going to use periodic boundary conditions. Let's remove the whole charge. Let's just assume that we're in a charge. We all have rho and j are 0. And let's just limit ourselves to second order finite differencing. And all the choices that I made here aren't necessary. And in fact, there is a branch. It's no longer called main. It's called tutorial_2021. But all of these choices are not made in another branch. Okay. The evolution routine is written with this very naive Python script that I showed you before. If you're doing something, if you're actually writing an evolution code, use NERPy instead, or something similar. Okay. And I have an appendix here. I'm not going to go over everything here, but these are common Cactus objects which you need to be aware of. CCTK, well, we'll see what they are. Sorry, it keeps flipping between that. We'll see these CCTK arguments are the arguments to our functions. CCTK LSH, as we talked about, is the logical size of our array. CCTK delta space is going to be our spacing. And there's a bunch of other ones that you can see here. And you can kind of see what they actually are supposed to do. Okay. Another thing we're going to have to worry about is scheduling. And so in this other appendix, I talk a little bit about some of the scheduling bins. Like base grid is where you set things that have to be set up every time a simulation is run. Initial is things which only have to be done at t equal to 0. Then there are things corresponding to AMR, which I'm going to skip over. Mol calc right-hand side are routines which fill in the right-hand side variable. And there's mol post step, which are things which you have to do after the right-hand side is filled in. And mol pseudo evolution, which is a group which we're going to use for constrained variables. Okay. So now that we've gotten some of the preliminaries in place, let's actually go about making a thorn. Well, so the first thing you would do, and we're not actually going to do this step by step, but the first thing you would do is you go to Cactus and you make new thorn. Okay. And I'll show you that for a second. So we'll just call this, this is not going to be simple Maxwell. This is just simple. And pick an arrangement. What the heck? I'll pick one that hasn't created yet. Okay, we're not going to worry about my email address. Okay, and the reason why I went through the step of using new thorn is because it created a set of files that are actually quite useful. These are the basic starting points. Most of them are basically empty. The thorn simple implements simple, and it doesn't tell you what it inherits or anything else. We have to do that ourselves. The schedule is going to be empty, so we'll have to fill in the schedule entirely by ourselves. But there are these files here, which at least we know we have to edit. Okay. So let's assume that we've made the new thorn. And in fact, we've made the new thorn, And actually, and we've committed it to some Git repo, like for example, which was done for this tutorial. And we followed the instructions. For example, here, we've essentially used get components to get that thorn. Let's see let's see what we had to do to make it actually functional. So simple Maxwell is actually the name of the thorn. And you can see here that I don't have anything in the configuration.ccl. I didn't need to make any changes, but interface CCL, we definitely need changes. Okay, so this is implements simple Maxwell, but one of the things it's going to need is the coordinates. So we better inherit from grid. That gives us our coordinates. And here's where we defined our vector fields: dx, dy, dz, bx, by, bz, and then this dot bx, dx, dy, dz, and bx, by, dz. These are going to be the grid functions which are going to be filled in with the right-hand sides for the evolution equations for d and b. And notice all of these are tensor type U, so they are vectors. But notice that the dot variables, those aren't going to be checkpointed nor prolongated. It won't be necessary to do that. Those will always be reconstructed when they're needed. Okay, we also have some scalars, and scalars also have time derivatives. And then we have what I'm calling constraint scalars. Those are actually the constraints of D and B, and we'll see that those are going to be constructed in a different time bin from the evolved fields. And then we have static fields. This is just the epsilon and the mu. And then I have what I call below standard boilerplate code. Okay, it's perfectly safe just to add this to every single one of your thorns. But basically, this is telling Cactus, I want to interact with the mole thorn method of lines. And in particular, I probably want to call these functions. Okay. And you might notice that we have the signature of the function and the function itself. Cactus will at least check if the signature that I specified here, I want to use this function, matches the signature from the function which actually provides, from the thorn which actually provides the function. And there's some other functions. Again, in the appendix, I talk about some of these functions which are going to be called. Okay, let's get to the schedule. So the very first thing we want to do is, if we're going to be evolving the Maxwell equations, we want to make sure that all our grid functions have storage. Now, in principle, we could declare that they have storage only when necessary, but in practice, there's no particular benefit of doing that, because these would have to be the evolved fields would have to be have storage at all times, anyways. Okay. So let's kind of look at this. Right now, this is actually conveniently enough in time order. We need to, in a group called mul register, we need to register our variables. This is where we tell mul that we have some variables, dx, dy, dz, bx, by, bz, etc., and it's going to need to evolve them. Okay, and this function is in C, and we have a little message which is going to be printed out when the schedule is printed out, tells us what this is doing. Okay. At the very start of the simulation, we're going to have to initialize our evolution variables, and this function, it's going to be the job of this function to do that. Let's ignore for the moment this options global and options local. They're going to be important when it comes to AMR. Okay, and then mul has a group called calc right hand side, and we're going to schedule some routines in that group. In particular, this function simple Maxwell right hand side interior. This code used to be a little bit more complicated. That's why this is being scheduled in a group, which is in another group. But there's actually only one routine in this group, so it was not necessary to do that. Okay. So at the moment, let's actually go, rather than continue going through the schedule, let's actually go to the code and see what these things are actually doing, what these functions are actually doing. So starting off with mole register, we're just saying that simple Maxwell dx, its right-hand side is called simple Maxwell dot dx for the rest of these. So that's pretty straightforward. And then also we want to register these constraint variables. So constraint variables don't have a right-hand side, but mole needs to know about them because so that it knows how to treat them. Okay, then we have an initial. And all initial is going to do is break my heart because I forgot to commit some changes. Okay, well, sorry, this version is not quite correct. I actually had updated this, but okay. So we have some type of initial data. We'll get to that and how you choose initial data in a moment. Sorry for moving up and down. But for example, here we're looping over, and by the way, there's a better way, there's a much easier way of looping over the variables, looping over all indices. I'm doing it this way, kind of shows you all the loops, but the Einstein Toolkit provides macros which will do the looping for you. Okay. So for example, I'm setting up this system where I'm setting side B and side D are going to be 0.
It seems we're having some technical difficulties with Yosef. Can anyone else, is anyone else experiencing the technical difficulties? Is Yosef frozen for other people? Can you raise your hand?
It's frozen for me here.
Okay, thank you. Thank you very much.
And he's dropped out.
He's dropped out. Wow.
Okay,
He's on power.
Yep. I'm sure he'll rejoin us momentarily. No worries.
Okay, not critical. Let's. One of the things that I've done here is I want to set my the initial values for epsilon and mu, and so I have a function which does that. Notice that, although I should have talked about parameters first, but I have a parameter called material properties. If it's equal to Gaussian, I'm going to call this function here, and this function will just fill in the material properties. You got I epsilon is 1 over epsilon, I mu is 1 over mu. Okay, I probably should have at that point actually done parameters. So basically the critical parameters for our code is that we have to specify kappa B and kappa D. This says it could kappa D could be 0 or greater, so it's positive, or non-negative. Kappa B can be 0 or greater. The initial data, that depends on what's actually implemented. And so I'm using this keyword, so you can give it, you can call the initial data by name. So compact pulse, random noise, things like that. And then we have some parameters which are going to have, for example, the wavelength. We'll see that a little bit later. It doesn't make sense for the wavelength to be 0, so we can tell it that it's non-inclusive of 0. And again, for widths, it doesn't make sense to have 0, so we can again tell Cactus that the number should be greater than 0. Okay. The other parameters I'm not going to worry so much about right now. Okay, almost there. Finally, the interior algorithm. And again, there are things I should just, I made a mistake. I should not have committed them. Okay, I'll fix it later. So we're going to need our grid spacing because we're going to be taking finite difference things. So you can see that where I construct dx, dy, get dx, dy, dz. And notice this is capital CC delta space. There is a lowercase CC delta space, but that is not what you want to use. Okay. Again, I'm being explicit about the looping. And here, like I showed before, this is where I'm finding the index in the array of the current point ijk, I plus 1, I minus 1, and j, similar for j and k. And here's where we calculate the derivative of bx, by, sorry, the three derivatives of bx, the three derivatives of by. So you can see this is, for example, this is k plus 1 and k minus 1 show up there, and bz, and then I'm just going to, same thing for dx, dy, dz, same thing for psi. Okay. And then here is where we actually fill in the right-hand side for bx. And this was actually all generated by that Python script that I showed you before. And so these are all the formulas for all the right-hand sides. And this file is done. Now, just in case you're curious, the only things that script actually generated were from this line down to that line. Everything else I just put in by hand. Okay, and then finally, we have the symmetry boundaries. We're just telling Cactus that at a certain point, you should apply boundary conditions to the D field, the B field, and the evolved scalars. And possibly at other points, apply boundary conditions to the constraints. Okay. So at this point, you've made your thorn. You probably want to try to build it. And I'm going to cheat a bit. So usually building Cactus takes a long time. It does. So I am just going to do a quick thing. I'm just going to delete the parts corresponding to simple Maxwell. Okay, and now I'm going to run make Maxwell. And this will check to see most of the thorns it does need to build, but it's going to attempt to build the Maxwell thorns. And fortunately, it didn't error out. Okay. Now, to kind of show this process from the very beginning, I'm going to make a new configuration. We'll call it Maxwell 2. And I'm going to set this up. It's going to ask me if I want this, and I'm going to say yes. This part won't take too long. We're not going to do much more. But now what I need is I need to tell Cactus which thorns are available, which thorns it needs to use. Within the tutorial, there is actually a something called config files or something called a thorn list right there. If I copy that into my new configs directory, Cactus will now know which thorns are required. So I'm not actually going to do this, but next thing I'd run is make Maxwell 2. And you can see that it starts and it's going to build it, and we're not going to wait for the whole thing to be done. Okay. So now that we have created our thorn, we've compiled it, we fixed all the compilation bugs. Now it's time to actually run it. And so let's look at that. Okay. And in fact, that's actually in a notebook. So I'm going to actually go to the notebook because it's a little bit cleaner. Okay. So we start off with a title. The title is not critical, but put it there anyways. And a few other things. Just for a test time, I want this to run for 60 minutes. Point of fact, the simulation I'm going to show you later ran for much longer than that, but we won't worry about this. And now I want to set up my grid. A few kind of standard boilerplate things I always put there. But I'm going to want to set my domain from chord base. And if I'm going to be using AMR, I have to tell it how many AMR levels there's going to be. I'm not going to be using AMR right now. And here's where I set up my grids. I just set up the extent in X and Y and how many cells for the extent. I'm going to be using periodic boundary conditions. So the boundary size will happen to be equal to the ghost size, which is, oh, that's actually a mistake. This boundary size should have been 2. Okay. We're not going to be able to see the bug in the actual simulation, in actual results, but the boundary size should have been 2, not 3. Sorry, it will, that bug will have no effect. Okay. And that's the sound of our grid, but our boundaries, we want to have periodic boundary conditions. And periodic boundary conditions are implemented in the periodic thorn. And we have to also give the parameter, you notice here, the parameter, periodic can do periodicity in either X or Y or Z or any combination of them or none. And so we have to specify that we want periodicity in all 3 directions. Now that we've specified the boundaries, we now need to specify the time integrator. In this case, we'll use RK4. And we'll specify the Courant factor. And then it's time to actually specify the actual evolution code. So our evolution code is simple Maxwell. And just, it doesn't need it, but let's just add dissipation to simple Maxwell as well. So there's another thorn which actually provides Kreisoliger dissipation. Whoops. So we could, sorry, I got to find, we could use that dissipation. And these are the variables we would need to dissipate. I noticed that I haven't set any parameters for simple Maxwell here. That's because the default values are just fine. If I wanted to specify things like a kappa D and a kappa B, this is where I do it. This is the initial data. It's going to be a compact pulse, which is moving in the Z direction. It's going to have a certain width and a certain wavelength and a certain width. And if we're worried about AMR, this parameter is going to become important. This tells it how to actually initialize the past time levels of t equals 0. Related to initial data properties are the material properties. I want a Gaussian distribution of dielectric. I want my dielectric to be at a particular Z location. And I want my dielectric to increase the dielectric constant from 1 to 1.5 at the peak of the Gaussian. And there'll be no mu will be just the standard, will be just the value 1. We're evolving this and things might go wrong. So let's check for nans in the evolved variables. And let's run some IO. And I can already see some things here that I definitely don't want to do. I don't want to do output 1D every 2. This is probably an old thing from a debugging a problem with the code. So that's definitely don't want that to be true. It takes time to do output. But we're outputting 2D every 16. You're going to see that that's a reasonable amount for this particular simulation. Some other parameters just to kind of fine tune what's happening with the output. Okay. And then finally, checkpointing. Because I set this to run for 1 hour, but it turns out it needs to run for longer than 1 hour. Okay, so I took that par file and I ran with it. Actually, I ran with it a few times because it didn't do anything really interesting the first time after just 1 hour. What you're looking at here is the output of the field dx. This is a visit artifact. This is not the XY plane. This is the XZ plane. And what you see here is the initial wave, at t equal to 0. And this is where the dielectric is. So you're looking at contours of constant dielectric. And let's see what happens. Okay. It seems to behave appropriately. The wave is being slowed down inside the dielectric, and there's seems to be some focusing effects. And everything looks okay. And in just a moment, you'll notice something a little bit odd. There's another wave coming, but that's because we insisted on periodicity. So whatever goes up the top comes back down from the bottom. So the wave is going to continue, and we'll eventually re-interact with the dielectric again and again and again. Okay. Well, that's my basic overview of the simple Maxwell tutorial, simple Maxwell thorn. At this point, I'd like to take questions. Oh, I had my video off. I didn't realize that.
All right, thanks, Yosef. Let's see, any questions in chat from the virtual attendees or here in person? Raise your hand if you have a question. So Yosef, can you explain again why there was an assumption of 2 boundary points? I thought when I looked at when you were showing the code, it had a finite difference stencil of width 1 plus or minus 1.
Right. So the dissipation would, let's see. So the core algorithm requires 1 ghost, so its dissipation should require 2. I specified ghost size of 2. Therefore, I should have specified that the boundary was with 2 as well.
Oh, okay.
So I think the net effect of that is that it's periodic on slightly different, at a slightly different periodicity than I might have expected.
I see. Have you run it multiple cycles yet? More than 1 cycle across the dielectric?
I was just playing with that, but so no. I mean, in the past I've run the previous example for a long time because I wanted to check stability, because you get to run into interesting instabilities when you include boundaries and electric charge. Mm-hmm. So I was playing with that. So I did run it. I have run this code for many iterations, but not this year.
Very cool. Oh yeah, Matt has a question.
Yeah. So suppose I was trying to run this not in a notebook, but on a supercomputer cluster. Would all those parameters be in some file that I would put in scratch space? And how would things work then?
Yes. I'm not sharing. Let me go back. Okay. So I actually did. I didn't actually run this on a supercomputer, but I did run it. Let me just see if I can get this to close. So the actual.
I'm sorry, I just feel so much more comfortable with terminals.
Yeah. So the actual. So I didn't use Jupyter to run it. First of all, I did use a par file. Okay, it's going to complain because of course it's going to complain. So in the run directory, I have my Cactus executable here and my par file. And so this is the thing I actually use. And that par file is in the repository edit anyway. And so this is the actual thing I used. I just copied this into the Jupyter notebook because I thought it formatted it a little bit nicer. But that's the actual thing I used. Actual par file I used.
And then when you run the Einstein Toolkit executable on an HPC, you would prefix that by something like an NPI run in a
right.
job.
Yeah, but that would be cluster by cluster, but sure. For example, S run something .cactus something, my par file.
Yeah.
So one thing that seems a little strange is, okay, so that parameter file, it seems like that's sort of the input file, the executable uses, but it's also, listing use thorns, which looks like a compiler instruction.
So, yeah, but the general thing is the general way that people would typically work is that they've compiled in more thorns than they're actually using. Because you oftentimes will decide, let's say you want to do some analysis later, so you think, okay, let's activate that thorn. But essentially, because you've compiled many thorns, and not all of them are active, you have to tell Cactus which thorn should actually be running, and only those thorns which are active, only their routines are going to actually be run.
Okay.
It's a little bit like in Python where you import what you need, and that's all.
It's not like a compile instruction, it's a run instruction.
Exactly.
No, it's a run instruction. This is basically saying, okay, make carpet active and make sure to run every function the carpet says to run.
Thank you.
Any other? Oh, yeah, Gabriel.
So you register constraints with your mole. Why is that?
Oh, because they have to be calculated at the right time. Essentially, if you want the and I think this one might be. I think I want to defer to Eric or Roland on this one.
Yeah, Roland.
So I can give you the technical answer.
Yes.
So the constraints depend on derivatives. Yes. Derivatives you can only really compute inside of the eval bit. You cannot compute them in the analysis bit. You will get the wrong answer. So they need to be somewhere in the eval bit, but they can't be anywhere random. So mole provides that pseudo evolution bit specifically to compute things that are not actually evolved, but are depending on derivatives. So it's just a convenience given. The name is a bit off because really nothing evolves, but they just happen to really fit in there. They really should be called evolution constraints or something like that. That's all there is to it.
But also there's, I mean, you're registering it. There's scheduling it, but there's also registering as a constraint variable.
Oh, sorry. After a question, then I guess. Basically, constraints here is something that comes out of the ancient times in the method of lines. So in principle, method of lines would let you mix things that evolve with the method of lines and some things that don't, that have their own time stamp. So constraint variables are just the ones that mole knows about and knows how to copy forward so that everything always shows up in time level 0. So normally, if you didn't have mole, actually the thing without any underscore piece, which you normally never use, that's the future. And everything that's computed before is an underscore p. And the constraint one basically makes sure that the things get copied forward from p to non-p at the correct times. So it's variables mole knows about, but aren't actually evolved by mole.
So is this how Hamiltonian momentum constraints are implemented?
Everywhere. I mean, if you leave them out,
Well, I don't remember where they're scheduled in lean and Bicol, but it's consistent between lean and Bicol.
I think it's
I think I did it in analysis, but I added some extra scheduling stuff to make it not completely crazy.
So what happens if they're scheduling the analysis?
you get the wrong answers every once in a while. Basically, yeah, the buffer zones aren't properly updated. That's basically what happens.
It's a mixture.
Yeah, the thing is, so it's not completely utterly wrong, but the thing is, the analysis bit in Cactus, so that's very technical, runs after you've done the restriction and everything else. And now you're computing derivatives in there. So the derivatives will now use the already restricted values, which is not what say happens for evolved fields, where you take the derivatives and evolve it, so they use the unrestricted values, and then afterwards the derivative gets restricted. So basically, you commuted derivative taking and restriction versus restriction and then derivative taking. So the answer is slightly different. That's basically why it's not done. And there might be special corner cases where you actually pick up poison yourself. Yeah, since they don't feed back into the evolution, nobody really cares.
Well, sometimes during visualizations, I think I would see there are final levels. So this might be.
This is probably part of it.
Could be.
But don't you run into issues also if you're trying to take norms of your constraints, because if you're putting things in analysis and the past time levels are not properly filled in?
Yes, that probably can also happen, because the order in which you would compute things would differ, because the things in eval, in the evolution bin, the course time levels step first, while in analysis they step last, or not last, but later. Let's put it this way.
Yeah. Well, for one thing, when I output diagnostics, I always do it every 2 to the n time steps to avoid any sort of time interpolation if I can.
Mhm.
Yeah. Otherwise, you can really get some weird looking results. But yeah, I mean, that's the Berger-Oliger algorithm. I mean, you can't escape to some degree.
Yeah. I think there's one specific case where doing the constraints analysis gives you the wrong answer, gives you poisoner. So it's either if you're outputting, it's either just that the coincides with the course one or just before or something like that. There's one point where it's off.
Interesting. Yeah. Cool. Yosef, I did have a feature request. Add a couple OpenMP pragmas. Or would that make it too complicated?
No, OpenMP. Are there OpenMP pragmas?
Yes.
Wait, I thought there are.
Oh, there was one. Roland saw one. Okay, sorry. I saw a couple that places where there wasn't one, but fair enough.
Oh yeah, I mean, initial data, I probably forgot to do that, but in evolution, there should be there. But yeah, certainly.
Yeah, maybe it was in the initial data setup or something.
Yeah, I mean, there's a few. There's a few anti-features I want to add, and that is because I've removed the row and the J, but I still have functions which calculate them, so that's not good.
Oh, okay. Yeah.
In fact,
Always
I'm not sure that the code that's in Git actually compiles. I probably should check that. Something got messed up. Like, I know for certain the code that I just downloaded is not the one that I compiled, because I know for sure I removed that set row from D function. Anyways, I'll figure this out and I'll make sure everything is correct by tomorrow.
Great. Thank you, Yosef.